The sound from a ship is reflected by a cliff. An echo is heard by a sailor on the ship 4 seconds after the sound is made. The speed of sound in air is 320 meter per second. All right, let's get some visual aid. Here's our cliff with the ship. Now, sound originates from the ship, travels all the way here, then comes back and is heard by the sailor. So if the distance from the ship to the cliff is d, the sound first travels this distance, then travels it again, right? Comes back, and it does all of this in 4 seconds. So velocity is given to us by distance over the time it takes, and velocity we know. It's in the question that sound is. This particular sound is 320 meter per second. Distance traveled is actually 2d. Just figured that out, and it just does that in 4 seconds. So simplifying, that's a 1, that's a 2. So we can say that the distance is actually twice of 320, and that's 640 meters. The correct answer is B, and yeah, easy does it. End X of a metal rod attracts the north pole of a compass needle. Which statement about the rod is correct? It is made of copper that is not initially magnetized. So copper does not respond to magnets. It's not attracted by magnets. So copper is kind of out. It is made of copper with the south pole at X. So you're thinking the copper with the south pole will attract the north pole, but copper itself does not attract or is attracted to any of the magnets. So copper is kind of out. Then we have the other two options which has steel in it. It is made of steel that is not initially magnetized. Okay. Yeah, just a regular steel, magnet will attract it, sure. It is made of steel with the north pole at X. So if the north pole is at X, it's still magnetized and it'll repel it. Another north pole will repel it. So the best answer is actually C over here. The diagram shows a circuit. Bam. So we see a battery is connected to 2 parallel resistors, straightforward. And the ammeter has 4 different range settings. Which range setting gives the reading near the midpoint of the range? Okay, let's first figure out what the current is, then we figure out what the ammeter is. So the total resistance over here is going to be half, because we have 2 resistance in parallel. So you can do 1 over 5 plus 1 over 5 equals to 1 over R, and you can figure it out, and you'll quickly realize it's just going to come out as half of this. So the total resistance, sum of these 2 resistors, is half of each of this resistance. And that makes sense, because if you think traffic wise, the cars are going in, and let's say only 10 cars at a minute can pass through. If you recreate this road on the side, so in total 20 cars are passing through. It's double the capacity now, or in other words, half the resistance now when you have 2 resistors in common. Kind of like a non-mathematical, a qualitative way of looking at it. Anyway, the total resistance is 2500, and the equation is V equals to IR. The voltage is 12, the current we want to find out, and this is 2500. The current will come out to 0.0048 amperes, and that's 1, 2, 3, that's 4.8 milliamperes. So how an ammeter works is just a scale, or at least the old ones, how they worked is just a scale from 0 to a maximum value, right? And what you can do is you have a knob that can change the maximum value. So if let's say the maximum value is 100 amperes, and the line is over here, and of course it'll give you a little more help if the pointer is over here. That's close to 50%, so the max is at a setting is 100 amperes. Your setting selected 100, so over here this should be very close to 50 amperes. So they're asking, well, it's a very weird question, but they're asking what will give you the reading in the center of this ammeter scale, or the midpoint of this range. So I mean, this being, I need to get this as the midpoint, that's 4.8. That's very close to 5, so this needs to be very close to 10 milliamperes. So my range should be from 0 to 10 milliamperes. 0 to 10 milliamperes, look at that. As if they knew what I was thinking. Right, the correct answer is B. In which example is the current 1 ampere? A charge of 0.1 coulombs passes through the resistor in 100 milliseconds. So it doesn't matter what it's passing through. Current is actually the flow of charge, flow of coulombs or charge per time. So which of these options is giving us 1? So that's the saying 0.1 charge divided by 100 milliseconds, which is 0.1 seconds. That's giving me 1 ampere. Look at that. So our correct answer has to be A. But let's look at B, C, and D. For B, let's call that A. For B, power equals to VI. We can kind of delve a little deeper, but I think it's straightforward. Just put it in the equation. The power is 0.1, right? And that is equal to the voltage, which is 10, divided by or times the current, right? And that'll just give you I as actually 0.01 amperes. So B is out. I mean, big shocker. Let's take a, with option C, we also see that V equals to IR. The resistor has potential difference, resistance 0.5, and the voltage is 2, so that makes I 4. So C is out, and that leaves D. And then 2 resistors with current 0.5 in a series. So if they're in a series, that's funny. I find that funny. The current in the entire row is just 0.5, right? In parallel, that could have been 1 in that circuit. So yeah, D is also out, and our answer is A. Which graph shows the relationship between current and voltage for a filament lamp? So the equation that brings it all together is actually V is equal to I times R. So current is on the y-axis, right? And this is on the x-axis. So let's rearrange this so it kind of looks like, you know, I equals to what's it going to be, 1 over R times V, where this is my Y and this is my X, and what is this? This has to be my gradient, right? So this looks like a equation of a straight line with no C, no y-intercept. That means y-intercept is 0, so it starts at origin. I'll give you one guess after this that what our correct answer is. It's actually D, right? D is our answer. A trolley carrying a strong magnet rolls down a ramp at constant speed. It passes through a coil as shown. So here's a small coil and is just passing. So EMF is generated or is induced in the coil as it passes through. Graph of the EMF is plotted. The experiment is repeated with many different coils and with steeper ramps. So essentially what they're changing is the number of turns and the steepness of this, right? The trolley moves at a greater constant speed on the steeper ramp, right? So it'll move faster on the steeper ramp, and so I guess they're trying to tell us it's at constant speed but faster. So maybe it's traveling for a while and has attained terminal velocity. Which graph is produced using the coil with least number? Okay, so the question is, they want to figure out that they're changing the number of coils, varying the coils, and the steepness of the incline, right? So with that in mind, we'll go to the answer. All right, so we see many graphs, and again we're talking about coils, coil turns, and steepness. Let's talk about steepness first. So the more turns you have, the more the steepness. If the steepness is higher, the cycle of the EMF generated will be smaller, because it does it very quickly, right? So it'll take less time to complete one cycle. So this will be very quick. So I see that graph C tells me that it's very steep, and D tells me it's very steep. What about coil? The more turns of the coil, the more EMF is generated. So higher turns give me more amplitude of the EMF. So this has fewer turns because this peak isn't too high, and this is also fewer, but that doesn't really matter. We have our selection of both over here, so the correct answer becomes C. Two identical objects begin to fall from rest. One object falls from 200 meters above the Earth's surface, and the other object falls from 200 meters above the Moon's surface. On the 1 second after they have started to fall, both objects are still accelerating, obviously. There is no atmosphere on the Moon, and the weight of each object is constant. So before this, no atmosphere on the Moon, that means there is atmosphere on the Earth, and hence there is air resistance. And the weight of each object is constant. This is interesting. I think most people can ignore this. It doesn't, make any, they wouldn't think too far. But some of the smarter people realize the further you are from an object, the gravity is lower. Like an astronaut in space doesn't really feel the gravity of Earth, if only he's closer. But closer to the Earth's surface, he feels it a lot more, even though if he's really high up, like on Mount Everest or something. But 200 meters for both Moon and Earth doesn't really matter. So they're saying for some of the smarter ones, weight of each object is constant, but in saying that, they probably just confused everyone else. Anyway, so here is the Earth's surface, and here is in parallel the Moon's surface, and the object in yellow is falling 200 meters on both, right? So which rule describes the motion of the object? So the motion, acceleration of the object falling above the Earth's surface, acceleration of the object falling. So we're talking about acceleration, right? So what's going to be the acceleration? As soon as they start falling, it's going to be 9.81 for this, and I think it's like 1.6 for the Moon, something like that. But there's no air resistance, so throughout its entire journey, the ball or the object will fall at that 1.6 meter per second squared, right? So throughout the journey, the acceleration will be constant. And over here, as soon as it starts moving at 9.81 or 10 meter per second. Let's go with 10. It starts with 10 meter per second squared. But as soon as it starts moving, air resistance starts coming in and starts slowing the ball down. But it's still moving, right? It's still gonna fall, it's still accelerating. But the acceleration itself, what's happening to the acceleration is that the acceleration will decrease. With air resistance, it's gonna be, we'll start reaching terminal velocity. So it's gonna be moving faster and faster, but the rate of speed pickup will slow down. So the acceleration will slow down and it'll be constant on the moon. Correct answer is A. An electron has mass, but it also has charge, right? So essentially, electron has a charge and a mass. That's the only two things an electron kind of has, at least for A-level syllabus, O-level syllabus, below the A-level syllabus, right? So whatever we care about. Where does a stationary electron experience a force? In an electric field. So it'll be attracted to a positive plate and be repelled by a negative plate, but that's not the only place it experiences it. In a gravitational field, yes, because it has mass, but not entirely, right? But in a gravitational field and an electric field, all right, I think we have our answer, right? What about a magnetic field? In D, we see a magnetic field. Will that electron experience a force? So we know a current experiences a force in a magnetic field, nothing else. I mean, current is something closest to the electron. What is a current? It's flow of charge. It is a flow of charge or rate of change of charge, right? Like current, electrical current, right? What do you mean by flow of charge? They're just moving electrons. What's interesting about electrons is when they're moving, they'll experience force, moving charge. One good way of understanding it is the Fleming's left-hand rule. So the direction of the current is important. If there's no direction in the current, then you can't really apply your left-hand rule. So a stationary electron is not pointing anywhere. That current for it, if it was moving, that would be considered current. But a stationary electron does not experience any force in a magnetic field. So this part is out. And our correct answer is C. The graph shows the temperature time graph for a sample of wax that is heated so that it melts. So it's solid over here. Now it's changing its state. We see that. And now it's liquid, right? The mass of the wax is 200 grams. So let's change that to kilograms. 0.2 kilograms. I think I said that right. The thermal energy is supplied to the wax at a constant rate of 12,000 joules per minute. They just can't not give us the value straight. They have to give it in a twist. Okay, we're better than that. We'll solve it. What is the specific latent heat of fusion? So what equation relates all these things together is, it's pretty obvious. The energy is Q is equal to mass times the latent heat of fusion, right? This is the total energy required, the mass. Like if you have more wax, it'll need more energy to melt it, right? So this is kind of relationship is helping us like that. So we know the mass, we just figured it out. Can we figure out the rate? So we know the rate. How much time did it take? So this is the amount of time it took for it to melt. This is the melty time. The melty time. What am I talking like? Melty time. This is the energy. Melty time, right? And this is where our change of state is taking place. Oopsie. The change of state is taking place. State of change. State change, right? This is the region. Okay, so you're provided, it's not on the graph, but in this amount of time, you're supplied this every minute, 12,000 joules every minute. So how much time is it? So you're starting at 3 minutes, so 2 and 4, so 3, and you end at 7. So this is 7, this is 3. So this time difference is 4 minutes. So you were melting or changing your state for a good 4 minutes, indubitably, right? 4 minutes. So what's the energy consumed by you, right? So it's essentially like, I went off on a tangent, but it's essentially 12,000 times 4. You consumed 48 joules in this time because it took you 4 minutes. Every minute you're getting 12,000. So 12 times 4 is 48, 40,000, right? That's the total energy you got. 48,000, wow. Okay, the mass was 0.2, converted that, latent heat of fusion, bam. And we'll get 240 as our answer. Actually, we won't get 240, but it's actually easier because it's joules per gram. So it's actually easier if we don't convert it into kilograms because we want our answer in. Yeah, sometimes it's actually nicer to look at the units, what they're asking, right before you get on solving it. Okay, so let's correct it with a different color, 200. And you should get 240.